Okay, thank you. Well, welcome also. My name is Susan Schwartz, and I'm going to be leading off the webinar on the potential of an Alaska amphibious community seismic experiment. What I want to do is to give you an introduction to the series of events that have led us to this webinar. And then throughout this webinar, we'll be discussing in detail various aspects of the timeline. So if I can see the next slide, it'll list the series of events that I'm talking about. And great. And you'll see that this journey started back in 2009 when NSF received American Recovery and Reinvestment money to build an amphibious array to be deployed in Cascadia in support of EarthScope and Margins, which is now the GeoPrisms program science objectives. If we go to the next slide, we'll see a little bit of detail that NSF received $10 million, with half going to ocean sciences and half to the earth sciences. And the ocean science money was used to build 60 ocean bottom seismometers, and the earth science money went to purchase land broadband seismometers to reoccupy 27 transportable array sites in Cascadia, and to upgrade 232 GPS stations that were part of the Plate Boundary Observatory. And this community-led open data access shoreline crossing project was actually chosen as number 65 of the top 100 ARA-funded projects. So if we go back to the timeline, we'll see that after NSF received this money, a small planning workshop was held in June of 2009 with EarthScope and Margins representation to discuss the important science targets that could be addressed in Cascadia, and then what would be the OBS capabilities required to achieve that science. In fall of 2009, work began to deploy the land instruments by IRIS and to upgrade the PBO, the GPS instrument capabilities by UNAFCO. And then in October of 2010, there was an open community workshop to actually plan the ocean bottom seismic experiment, part of the Cascadia, what was called the Cascadia Initiative. And at that workshop, there was a call for people interested in being principal investigators to actually make sure that the OBS deployment that was determined to obtain the science objectives, right, that were first outlined by that initial planning group, but were fleshed out by this big open workshop. There was a call for that, and by fall of 2010, a group was put together to actually go out and make sure the to deploy the instruments, and that group was called the Cascadia Initiative Expedition Team. And then that next summer, July of 2011, the first OBS instruments were deployed in the Cascadia, offshore the Cascadia region, and those deployments continued for 4 years through the fall of 2015. And it was a lot of work. In those 4 years, each year required about 6 different cruises, 3 to deploy the instruments and 3 to pick them up. The first data came back from that initial deployment of instruments. That data came back in fall of 2012 and was archived at IRIS for everybody to access and use. And this went on for the next couple of years. As data became available, it was also added to the archive. And by fall of 2014, it was felt that there was enough information to actually try to assess kind of the success of the Cascadia Initiative and to think about what is the future for this amphibious array facility. And so the fall of 2014, this community experiment took place, and the key questions that was the focus of this workshop was what science actually requires an amphibious experiment, that is the simultaneous deployment of both the land and ocean instruments. And what would be the appropriate size and scope and even locations for a future amphibious array facility deployment. And through the rest of this webinar, the presentations that you'll hear will be covering the content and the outcomes of that workshop. But let me just summarize and tell you that the consensus was that the Cascadia initiative was seen as very successful, and that there was great value in the community experiment approach. And also there was a strong desire that came out of that workshop to use the amphibious array facility simultaneous with the transportable array instruments that were going into Alaska to target important science problems in Alaska. But despite that community consensus, NSF made the decision to actually dismantle the amphibious array facility and to take the instruments that constituted it and put them into the general pools, the land instruments into the pool, the Pascal pool, and the ocean bottom instruments into the opposite pool. But they did find in the report very compelling the idea of having an amphibious community experiment take place in Alaska, and they released the Dear Colleague letter soliciting proposals for that community amphibious seismic experiment. And so that is the focus of this workshop, is really to talk about that potential. So I'm going to turn it over to Jeff, and he's going to drill into a bit more of the details of some of the aspects that I briefly covered.
Thanks, Susan. No, that set the stage well. So what I'm going to do is talk about what came out of this workshop that had as its two goals to evaluate what happened in Cascadia and to think of how this worked well and how in the future we could do a better job, and also start down the line of talking about some of the recommendations for future amphibious seismic studies. The next two presentations will go into the science in a bit more detail from that report, and specifically focus on Alaska, as you'll see. Sort of a majority view from this workshop was that there's a tremendous amount to be done in Alaska, and so we're leading up to that. And I would say, just to keep the suspense down, so where this is going is in response to, I know, this open call from NSF through a Dear Colleague letter for community experiment in Alaska. We're taking some of the first steps to do community building. If you stay tuned till the end, we'll show you where it is to go next, what we expect to be some of the next steps toward bringing people in to have as open a process as possible to actually respond to these calls for new community experiments in advance of the summertime deadlines. Okay, so Amphibious Array Facilities Report, as Susan said, came out in 2015. You can download it on the GeoPrism, Xeriscope, IRIS, and I think NAVCO websites. The workshop was really about the science justification for doing something new, and focused on three critical systems for which amphibious work was seen as necessary. One was looking at subduction processes that cycle material, build crust, and produce magma and volatiles. One was looking at passive margins and transform faults and the hazards they produce. And the third one is looking at seismogenic processes, particularly along the megathrust at subduction margins. And it was seen right away that at least two of these three have a lot of geographic overlap in where you would want to do this. So, and it was felt like Alaska Aleutians would be the next obvious site to do this. So first I'm going to do is talk about what happened in Cascadia. As Susan said, there was a 4-year, 4-stage deployment plan. The map that you see on the right shows, well, a lot of things. Shows the Cascadia margin, the Juan de Fuca plate, and in little squares are places where seismometers were placed. There are land seismometers in white and yellow that stayed throughout the whole array. They were sort of a reoccupation and densification of the transportable array. And then the offshore part was deployed in sort of 2 or 3 geometries. There was essentially an extension of the transportable array 70-kilometer spacing, covering the entire Juan de Fuca plate and actually across the ridge to the Pacific plate side. There was densification all along the megathrust at one scale, and then in two patches, Grays Harbor, Washington, and Mendocino Triple Junction, there were dense arrays that were put out. The first year was really to some extent a pilot year, and that a lot of the instruments were being tested for the first time. But then, but by year 3, I think the operation got to be fairly robust. Data recovery became fairly good. The geometry then was 2 years in the north, 2 years in the south for the 70 or the 60 Cascadia OBSs to be deployed. The land array stayed fixed through the whole time, and so provides sort of a backbone. These are just a couple of slides of pictures showing, well, what essentially a transportable array land station looks like, what some of the standard OBSs look like. All 3 of the OBSIP providers, Scripps, Woods Hole, and Lamont, all participated and contributed instruments, all received RF funding to develop new ones. They're showing Scripps and Hui instruments. One of the, I think, probably the main new innovations that came about this instrument building was the development of the first instruments that are really designed for use in shallow water. These are very heavy, what are called trawl-resistant mount instruments that did 2 things. One is that they're low profile and heavy weight. They're shown here in this picture. They're resistant to bottom trawling, and there's some evidence that they were not picked up by bottom trawling. But probably at least as important, these have turned out to, by being heavy, not having so much exposure in the water column, to be much quieter at a lot of the frequencies that shallow water OBSs have been noisy, particularly in the broadband longer period range. So these have made shallow water data much more useful, especially horizontal components. So that's the new instrumentation. We because of the sequencing, the first data, although it's been out for a couple of years, the first full data sets have only been available probably since late 2014. We've already seen a number of papers come out. There was an overview of the array in Oceanography in 2014. Notably, there's a special issue of Seismological Research Letters that had 7 articles that started looking at the various aspects of array performance. And before and since then, there have been a number of articles on sort of some of the exciting things that you can do now that you're sampling seismically an entire oceanic plate with anisotropy, imaging, with ambient noise, various other issues related to things you see on the seafloor. And importantly, there's a number of new papers that are in the works, funded projects. There was an OBS workshop last October. There's a ton of new posters and presentations that suggested that we're going to see a lot coming out of this. One of the things that the workshop was charged to do was to provide some technical recommendations about what worked well and what to emphasize. There was a list of, you can download the report to see all the recommendations. A couple of the important things, I think. One is that having these shielded OBSs as the trawl-resistant mount ones, and there was an abalone design as well, did a lot to reduce shallow water noise, particularly in horizontal components. Has made there have been a lot of questions about using intermediate to long period OBSs in this environment. They're still noisier in many cases than land instruments, but there's certainly much more useful information in them. Having pressure gauges, high quality pressure gauges attached to the OBS allows noise reduction, principally through removal of infragravity wave signals, looking at seafloor compliance. One thing that came out of this was the realization there's probably a better way to phase these things. If you could deploy for 15 to 18 months rather than the less than a year that was deployed in Cascadia, and new batteries should allow that, you could put instruments in, say, late in the spring, early in the summer of one year, let them run through 2 summers and a winter, getting not quite double the data, but much closer to double the data than the Cascadia deployments for essentially half the number of cruises. And then this would allow a winter afterwards for instrument recovery, repair, and upgrading and so forth. And so it felt like not only would you have instruments that were in better working shape, but you would be able to run these things much more cheaply. And so that's something that we're looking at for any future deployment. The onshore data, having them tightly coordinated was in great value. There was actually an extra onshore deployment on Mendocino Triple Junction to take advantage of having the array there. We haven't seen what's come out from that yet, but that seems like that's going to be really important. Another thing that did not happen in Cascadia, but was seen as greatly desirable, was somewhere in the mechanics of collecting and processing this data to try to ensure that there was some kind of integrated seismicity catalog as a, a basic low-level product that everyone would have access to, just to help people into the data. One of the things that I think was most exciting about this, sort of from a broader perspective, was the tremendous growth of the community that was looking at marine and onshore offshore data. All the cruises included mechanisms for first-time early career scientists to participate, to go to sea. Workshops were held both to help plan the experiment and to look at the data. So there's a lot of, so the experiment was planned in a way that there would be a lot of interest and a lot of exchange of information as it was going. And one of the main things is by having data open, all the data became open as quickly as sort of time and other corrections could be applied and it could be put in the IRIS Data Center. There's tremendous growth in the community. So this is a plot from Doug Toomey's 2014 overview paper of the project, where it's showing that the number of unique users just over sort of the first year and a half of the project grew up to several hundred during this time period. This is before even any papers had really been published on this. And a lot of these people are not people that ever really used OBS data before. We're seeing a lot of new young people. So it seemed like there's a very effective mechanism for getting, a lot of scientific bang for your buck and a lot of participation in use of, what's a fairly involved facility. The part then looking toward the future, of course, as Susan said, it makes sense to use this kind of, whether you want to call it a facility or grouping of instrumentations, to study systems in nature that are complex and require simultaneous onshore and marine observations. One of the things that was highlighted, at least for the next couple of years, is to leverage other resources, in particular the EarthScope US Array Transportable Array, which is right now ramping up operations in Alaska and will be there for the next few years. And that was one of the big pushes to do something in Alaska, as well as to build on science plans from EarthScope, from Geoprisms, and some of these other kind of community organizations. There's also seen, because a lot of major natural hazards occur crossing the shoreline, there's tremendous potential for addressing issues of societal input and natural hazards. And again, if you look at the three critical systems, looking at subduction systems that naturally cross the shoreline, looking at subduction systems in Alaska, leverages the EarthScope transportable array, seemed like a real natural fit. And so there's a fairly strong consensus at the workshop that this would be the next place to go. So the next couple of talks will go into the systems in more detail, but just as an overview map, the Alaska Aleutian Subduction Systems is one of the world's great subduction systems. The pink patches on this map I'm showing are the rupture zones of the great earthquakes that have happened over the last century, including the 1964 Good Friday earthquake, the second largest earthquake ever recorded. There's a tremendous history of that. There's also a tremendous volcanic history. The black triangles show active and recently active volcanoes up and down the arc, from the far western oceanic arc to the continental arc in the east. So there's tremendous opportunity for that. The infrastructure that's being added then is also worth looking at. What I'm showing now is a map showing the US Array Transportable Array deployment and deployment plans. This is maps now about a year old, so this may have changed in some detail, but essentially what you can see through the colors is that red and yellow stations were to have been deployed by last year, the green ones by this year, the blue ones by the end of summer 2017, and so this array should be up at full strength then. The ramp down is not yet clear. It's not yet funded how that's going to happen, but it should happen sometime after 2018. We expect to see it, like elsewhere in the U.S., on the order of 2 years of full network data recovery. Better than that, a lot of the stations, maybe all the stations that are within a few hundred kilometers of the subduction zone margins, are very high priority for other reasons. Many of them already are permanent stations that have been upgraded. A lot of these others, there's been a lot of interest on the part of the Alaska Earthquake Center and other groups to adopt them. And so the hope is that actually the southern part of this array can continue operating for a lot longer. But regardless, there's this tremendous opportunity with such a dense array to do all sorts of things if we can deploy offshore to complement this onshore array. Sorry, wrong way. This map is showing, I have two maps showing some of the existing data offshore. This is showing a lot of the active source lines that have been done over the last couple of decades. Edge and TACT are sort of getting back to the 80s. One line in the 90s off the ASE spanning the Bering Shelf, and a couple of transecting Aleutians. And most recently in 2011, the Aleut cruise connected a series of transects across the Alaska Peninsula margin. This is one of the target areas a lot of people are thinking for this proposed array. There's also the steep array in the late 2000s offshore in the Gulf of Alaska. If you go to the IRIS DMC and look for seismic stations from Pascal, temporary arrays that have been deployed, this is what's there. There's been a series of transects going all the way from the Gulf of Alaska to the Bering Sea coast and up and down the arc here and there. So there's a lot of sort of onshore things to compare to. What this does not include, this map, are data that are just now being collected. And there have been a number of experiments that, at least that I know of, that have been funded and that have instruments that are either in the ground now or going in this summer. These include salmon across Cook Inlet, wolf across the Wrangels, flats across, sampling some interior basins, AAA, and several others sampling volcanoes farther out in the arc, and so on, as well as there's the permanent network stations that are showing. So there's a lot of onshore infrastructure to tie to. The key is to get offshore and, sorry, I keep getting around, but look at what's. So the last slide I was going to show you is just what the workshop report came up with. You'll hear more about this in the next couple of talks, but there was the Subduction factory group targeted sort of two corridors, one off the Alaska Peninsula where the continental arc is subducting, one farther west across the oceanic arc. Maybe that's something to think about for later, but the first one to some extent overlaps with where the megathrust, megaswath transects were also proposed to occur. So I'm going to stop there. I'm going to turn this over now to Emily Rowland, who's going to talk about that last thing about the megathrust. So Emily, just say next slide whenever you want to continue here.
Okay, thanks, Jeff. And yeah, you can go ahead forward. There we go. Okay, so in terms of science goals, the Alaska margin, as we all know, is very well suited for onshore, offshore studies of seismogenic processes at subduction zones. So here, figure on the left, just to get us started, is Jeff was just showing some equivalent to this. This is now kind of zoomed in on the Alaska Peninsula region and south central Alaska portions of the margin. So with the exception of the Shumagon segment, the entire subduction zone has ruptured in great earthquakes in the last 100 years or so. And the Shumagon and Samiti segments, highlighted on the right, represent one location where there appear to be a significant change in plate locking behavior over a relatively short distance along strike. And so in particular, you know, part of what makes this margin so useful for these onshore-offshore studies are the significant interseismic seismicity rates, these types of changes in seismogenic behavior along strike, good information on upper and lower plate structure, and then, of course, adding on top of that this kind of recent synergies with the Earthscope array in Alaska. And so, in particular, you know, as this figure on the right is illustrating, the Shumagon segment, you know, and the Samiti segments, just as an example, to the left here, the Shumagon segment shows coupling shows low coupling, higher seismicity rates, including events we believe are occurring on the plate interface. By comparison, the Samiti segment to the east is almost completely locked, has frequent magnitude 8 earthquakes every maybe 50 to 75 years, so really frequent. In including the 1938 magnitude 8.3 event, and shows lower seismicity rates. And so this is a pretty significant change in both interseismic seismicity and coupling that's happening over a really relatively short spatial distance along strike. The other thing to highlight here, just again using this Samedi to Shumagen segment as an example, is that really there's many places like this along strike in Alaska where seismicity rates are really high, as I mentioned. In particular, for a, say, year-long deployment offshore there, dealing with these kind of shorter-term deployment timeframes associated with ocean bottom seismometers, we would expect to observe, 1,000 or so magnitude 2 and greater earthquakes, 10,000 magnitude 1 and greater earthquakes. And so this is really a big difference over other recent offshore kind of large-scale community experiments like the Cascadia Initiative data, and I think could provide a real opportunity to make some new types of observations using lots of earthquakes as data points in Alaska. Next slide. All right, Jeff, you can go forward here. All right. So in addition to kind of large earthquake ruptures, there's also lots of examples kind of even outside of this Shumagen-Samedi example where in terms of identifying controls on locking behavior and specifically the relationship between earthquakes, slow slip, and tectonic tremor, there are several places where there appear to be interesting changes in fault slip behavior accompanied by tremor or low-frequency earthquakes. And so here are a couple of examples of, first on the right, deep tremor and low-frequency earthquakes down dip of portions of the 1964 rupture area. So on the far right, this is an area down dip of the Prince William Sound disparity where there's been some really interesting observations of kind of slow slip transient events that are accompanied by tremor kind of below the seismogenic portion of the megathrust. And then in the kind of center of the slide there are examples of low-frequency earthquakes kind of down dip of the Kodiak segment. And I think there's been even significant recent, even more recent work in that kind of Prince William Sound area identifying some really unique time-dependent changes in plate locking behavior there. Similarly, on the left, now working farther to the west, is another example of a pretty different part of the margin towards the Unalaska and Akutan Island region. So this is now west of the Alaska Peninsula, where there appears to be a particular hotspot for tremor activity, possibly also associated with a change in plate locking behavior. Though I think it's unclear, at least to my knowledge, that we can characterize at this point how far up dip this tremor extends, and so that leads to questions of sort of what part of the subduction zone is this tremor activity occurring in. Is it, again, sort of down dip in this transition zone area, or does it extend kind of throughout the typical seismogenic zone depths? All right, we can go forward. Thank you. And so in the context of seismic observations in Alaska, I think it's also relevant to point out the prevalence in some regions, especially of downgoing slab events. So here I'm showing you results from the Moose experiment that Jeff showed a couple slides ago. Again, this is in the Prince William Sound area on land, where it appears to be that the majority of interseismic earthquakes are occurring within the downgoing slab, so they're occurring as downgoing slab events, with few, if any, we think at least in this region, occurring on the plate interface. And so this is both, relevant for kind of understanding, again, how this part of the subduction zone is behaving in the context of locked versus slipping behavior. Strain accommodation, Jeff, you can go on to the next slide. But it's also relevant, for other reasons. If you've lived in Alaska, this is of daily relevance. Slab events are commonly felt in Anchorage. And here, so this is January's Niska Earthquake, magnitude 7.1. This was one of these downgoing slab earthquakes. And it really highlights that these downgoing slab events can be large, with large magnitude. It's relevant for hazard characterizations, as well as potentially these events provide a really great opportunity for imaging the overlying mantle wedge and kind of upper plate structure. All right, next slide. Okay, so in considering where and how an amphibious experiment would be kind of best designed to expand our understanding of the link between margin structure and fault slip behavior. There's been significant recent work in Alaska, in this portion of the Alaska subduction zone, in key locations along the margin that I think provides new insight into the detailed geologic framework, as well as possible sources of structural or material heterogeneity that might be controlling the rheology of the plate boundary and kind of how fault slip is being accommodated along strike and up and down dip and along the Alaska margin. So here on the right are some recent results from the Aleut refraction active source experiment. And so this experiment was, as Jeff showed, was spanning the Samiti-Shumagan segments. And so what we're showing here is that this work was used to identify changes in bending faulting associated with pre-existing downgoing plate fabric, so fabric of the Pacific plate. And these changes in bending faulting appears to lead to increase in hydration of the downgoing plate, and so that's what's being shown in that kind of seismic velocity image on the lower right. So increased hydration of the downgoing plate within the Shumagan segment specifically as compared to the Samiti segment. And so again, this might be telling us something about kind of how the physical properties of the downgoing plate ultimately could influence kind of subduction zone and seismogenic processes along this transition in plate slip behavior. In the lower left, on the other hand, or in addition to this, there's abundant legacy MCS data. Again, I think Jeff showed a couple slides that highlight the locations of some sort of famous at this point legacy MCS data sets, including the edge and the TAC transects. Here, this is a line drawing from the edge line, which is kind of closer to the Kodiak asperity, I think. I don't show a map here, but these types of data provide insight into changes in sediment supply, margin framework, and faulting at different locations along strike. And so these, I think, will be useful in kind of having some structural context to earthquake observations and other imaging studies that are done with the future amphibious deployment. Okay, next slide. Okay, furthermore, in terms of the plate boundary itself, there are also significant recent new insights into plate boundary structure from both active source and teleseismic or receiver function imaging. So on the bottom left, again, this is now results from the MCS data from the Aleut experiment in the Samiti segment that's been used to identify clear changes in reflectivity structure of the plate interface. That's what's being shown in the kind of different colored lines there. Possibly these are associated with changes in subduction, in subducted sediment, and changes in the kind of downgoing plate interface shear zone as it transitions from the seismogenic portion to kind of the down dip or transition zone area. On the upper right, then, we're showing deeper plate boundary structure that kind of spans between the coastline in Prince William Sound and Central Alaska using the Bear and Moose data. And so these are receiver functions and teleseismic migration images of a low velocity layer that we think is at the top of the Yakutat slab with reduced VPVS ratios, potentially indicating that plate interface material is influenced by subducted sediment and or high pore fluid pressures in this region. So it's just worth mentioning, related to sort of these types of imaging experiments, that although receiver functions, for example, have been mostly limited in the past to locations on land at subduction zones, there have been, this is an example of a type of work that's been done kind of for the first time using Cascadia initiative data, specifically the kind of shielded, the noise shielded troll resistant mounts. It's been done for the first time offshore to determine similar information about plate boundary structure using receiver functions and kind of past the coast. So this is, I think, a real possibility, a good target potentially for learning about the subduction zone, maybe further west, for example, in Alaska. Okay, next slide. Okay, so to wrap my portion up here, I just want to reiterate that Alaska has many really key attributes for a big, large-scale deployment focused on questions of seismogenic processes at subduction zones. So, you know, the basic aspects of abundant seismic activity, variable slip behaviors in space and time, and pretty good knowledge on existing geophysical framework. And so keeping in mind some of our goals, and I'll kind of touch on those in this very last slide coming up, it'll also be important to, you know, be planning for some potential new challenges. So for example, with the figure on the upper right shows, Jeff mentioned this already, but it's really likely that we, in a year-long or 15-month-long deployment, will observe, you know, maybe several magnitude 6 events in relatively close range, almost no matter where we are along strike. And so, you know, being able to, for example, observe those larger magnitude events on scale, I think will be a really important thing to be planning for at this stage of the game. You know, we also might be thinking about whether, in terms of characterizing deformation, do we need absolute pressure gauge sensors at certain locations or all over where our deployment will be, you know, onshore, or at least in the offshore regime. And yeah, go ahead, next slide. And so again, here's this image of kind of where we have some interesting insight into the margin from past studies in addressing some of the most central or some central scientific goals, such as, you know, what explains variability in slip behavior and seismicity patterns along strike, or how do physical conditions influence seismogenesis. I think, you know, it'll be important to be designing an array that has station spacing dense enough to characterize the thrust zone, and, you know, and locate events well along the plate boundary, and determine good depths in particular. And so you can go ahead to the last slide here, Jeff. Yeah, and so here I'm just plopping on top of this in kind of cartoon form a couple of these these transitions from locked in sort of red to potentially less well locked or more slipping sections along strike. And so when we consider, you know, some key kind of corridors for a future deployment that captures some of these transitions, we may need to be considering sort of the spatial extent that we're actually able to achieve while still maintaining these goals of characterizing the thrust zone well. And so if we, for example, want, you know, station spacing that is 1 to 2 times the depth to the plate boundary interface, at least within that kind of offshore forearc region, we might be aiming for, you know, 20 to 30 kilometer type spacing that would potentially, at least for subduction zone questions, limit the extent to which we're able to really sample the margin. And so this is going to be, I think, a big challenge and an important thing for us to be considering as we hopefully move forward with some proposed plans for an offshore deployment or onshore offshore deployment in Alaska. Is, you know, how much of a spatial extent and where are really the most important targets for us to focus on, maybe a couple hundred kilometers along strike in this region. And then, of course, finally, you know, designing this with consideration with where the most kind of complementary TA observations are going to be located and where there have been other recent data sets. And so with that, I think we'll maybe move on to discussion from Doug of Subduction Factory type science goals.
Hi, this is Doug Weens. You can go to the first slide here immediately. Yeah. So I'm going to talk about some really exciting problems, I think, in fluid and melt transport and cycling through the subduction system that we could address in Alaska. And so I'm going to be highlighting at least three topics that I kind of pulled out that we could, I think, make a lot of progress on in Alaska, in many cases building on work that's been done in other arcs, as well as previous work in Alaska. So the first topic will be how much water is input on the incoming plate and then subducted to great depths in the subducting plate interior. And this is a big question not only for the shallow systems that we're looking at, but for the larger scale cycling of volatiles in the Earth. Second one will be the distribution of melt in the subarc mantle and how that relates to along strike petrologic and tectonic variability in the volcanic arc. And then finally, I'll talk about the process of releasing fluids from the downgoing plate. Of course, that's what kind of initiates the arc volcanism. But how are the fluids released from the downgoing plate, and how is this related possibly to intermediate depth seismicity? Next slide. So this figure, I'm just showing this figure from Hacker and some reference to Van Kekken's work here, is just to illustrate really how important this problem is how much water is going into subduction zones in the incoming plate mantle. And if you kind of decipher all these arrows on the left here, what you see is that there's a lot of sources for water in the shallow crust and mid crust, but most of this water is released at very shallow levels, or at the deepest level, it's released in the arc due to the heating up of the slab and the dehydration that occurs on the very top of the crust. But the real question in terms of the deep subduction of water is the mantle, and how much water is actually entrained in the mantle and taken to great depths. And what we have at this point is only very, sort of, I would say, gross estimates or even wild guesses in terms of the amount of water that's being carried into the Earth's into the deep mantle in the subducting plate mantle. And so that, I think, is a fundamental question. The leading candidate for possibly hydrating the mantle, for years people, I think, felt like the mantle probably was not hydrated and was relatively depleted from the oceanic crust formation at the mid-ocean ridge. But the leading candidate now for hydrating the mantle is fluid circulation along plate bending faults as the incoming plate approaches the trench. And there's just a little figure here showing a thermomechanical model where we do hydrate a lot of the plate by circulating fluids along the plate bending faults. The water reacts with the peridotite of the mantle to produce serpentine hydrous minerals. Next slide. So when we think about how important this could be, one of the questions is how widespread are earthquakes, and do they actually fall within the mantle? And there's been a number of teleseismic studies, and even in a couple of ARCs, local studies with OBSs that show that these normal faulting events on the incoming plate actually go well into the mantle. And the histogram here shows that most of them occur in the upper maybe 10 to 15 kilometers of the subducting plate mantle. And just making sort of really rough order of magnitude calculations in terms of if these faults do cause serpentinization of the uppermost incoming plate mantle, one can easily multiply the global water input into subduction zones and into the deep mantle by a factor of 2 or 4. So this is a really important question. Next slide. So, and I think Emily already showed some of this work, but this work by Donna Shillington really shows that the Alaska Trench is really an important place to study this process, because she used seismic imaging, active source imaging along 2 segments, the Shumigan segment, which is not characterized by large earthquakes and seems to be slipping aseismically, and the Smeedy segment, where we have had previous large underthrusting events. And what she found was that in the Shumigan segment we have this fairly large region of reduced upper mantle velocity on the incoming plate, local right around the trench axis, in the same place that we see lots of bending faults forming in the plate. And that suggests that the uppermost mantle is being serpentinized. It's being hydrated there by fluids along those faults. I mean, there are some questions here in terms of how much of the velocity reduction is due to actual serpentinization of the upper mantle, and how much could be due to just the formation of cracks and the input of water along those cracks. You know, so there's a lot to be learned, I think, but it suggests that there is this fundamental difference between these two segments, which you can see even in the morphology of the seafloor, where the Samidi segment has very few faults, and the Shumagan segment has a lot of large faults. There isn't the connection here seems to be with the seafloor fabric coming in, because the Samidi segment has a different orientation of seafloor fabric and faults that have already formed on the seafloor at the mid-ocean ridge coming into the segment. Next slide. Okay, the second topic I'm going to briefly discuss here, and that I think is really exciting in Alaska, is study of the arc velocity structure and mantle melt production. And I'm showing here just a figure from the Mariana Arc, because there hasn't been a lot of imaging of with a dense enough array of the volcanic arc in Alaska. But in the Mariana Arc, we've imaged the velocity anomalies in the uppermost mantle beneath the arc, and in this case there's an active back arc spreading center, and so we see very robust slow velocity anomalies in the upper mantle beneath these volcanic regions. And in particular, I think what's really exciting about this work and about some of the work that's possible in Alaska is that we can put the seismic images together with many other things that we already know about the volcanic arc. And in this case, we could compare the depths where we see the seismic velocity anomalies with the inferred depths of the arc magma production from thermobarometry, from petrology and geochemistry, and we can show that where we're imaging these large anomalies is precisely the depths at which the arc magmas had their last equilibrium depths. So that shows clearly that we're really imaging the arc magma production region, which offers these tremendous possibilities then of comparing what we're observing in terms of the arc melt production system in the mantle with geochemical and petrological volcanological constraints on what's happening. Next slide. And another kind of interesting thing illustrating this issue of a long strike variability is from this work in Central America, where Kate Reichert found a much higher seismic attenuation in Nicaragua than in Costa Rica. And there were also differences, I believe, in the velocity structure in these two areas. This correlates with differences in fluid mobile elements from geochemistry and petrology that suggest that the Nicaragua mantle wedge has a much higher water content than the Costa Rica mantle wedge. And so this is a nice example of how we can use mantle imaging to complement studies of how the volcanic arc is operating from other fields. Next slide. And the last topic I'm going to mention here is this issue of what happens to the water once it's subducted. And these are images from Stéphane Randonnet's work with scattered wave imaging of central Alaska. And what you see is this subducting crust, which is shown in red here, and it starts out quite thick because there's thickened crust in this area, but becomes thinner with depth. And the inference here is that, and this is borne out by, or suggested also by thermal calculations, that this thinning of the crust involves the actual dehydration and metamorphism and eclogitization of the downgoing crust. And then eventually, of course, at about 120 kilometers depth, the crust image, signature actually is gone, and we believe that the entire crust is probably transitioned to eclogite by that depth. But another interesting thing here is the relationship of intermediate depth seismicity to these reactions that we think are going on in the crust. And in this case, the intermediate depth seismicity seems to occur where we are seeing the metamorphism and eclogitization of the crust, and then goes away. Intermediate depth seismicity goes away at greater depths, and that's consistent with the with the likely importance of water given off by the dehydration reactions in forming the intermediate depth earthquakes. But the whole issue of what causes intermediate depth earthquakes, I think, is still somewhat open, and higher resolution images of both the seismicity and the subducting crust in Alaska could really, I think, push this this area forward. And so that's all that I have, and I think we're now going on to Rob Evans.
Okay, just on mute. Okay, can you hear me? Okay, you can move forward to the next slide. I don't have a whole lot to show here. I wanted to sort of put what may or may not be done in Alaska through the use of MT and electromagnetic methods in the context of the TA that we're talking about. And from the first point is that there is no MT-TA work in the current EarthScope budget. So one thing that this this opportunity might afford us is the chance to look at doing some of that and actually collecting some TA-like MT coverage across Alaska. The map that's shown there shows what does exist in Alaska. The black dots are legacy data, which are probably not recoverable. Maybe, it's hard to say. The green dots are much more recent work, combinations of efforts by the USGS, in particular the fairly dense grid of coverage in southwest Alaska has been done by the USGS recently. There's been some other work that Adam Schultz has done in more sort of central Alaska that's been part funded by EarthScope as FlexArray, but also with interest from space weather community. Mentioning space weather, there are some efforts underway to look at completing the MTTA across the lower 48 and maybe in Alaska as part of a national effort to identify threats to infrastructure from large geomagnetic storms. So, from the point of view of MT and EM, we can address pretty much all of the targets that the previous speakers have covered. Fluids in the incoming plate and upper mantle, release of fluids from this downgoing slab, melt generation, and transport. And I'm not going to give examples of all of those, but I am going to just spend a little time talking about fluids in the incoming plate. So if you go to the next slide, please. And this is an example of some CSEM work, which is maybe a little bit different to some of you. MT uses just naturally occurring fields. And we measure those fields passively with instruments either on land or on the seafloor. With CSEM, we're generating we're transmitting a signal from a source which we tow behind a ship and transmit to seafloor receivers. And so, this is the example from the Nicaragua system that I did with Kerry Key and Steve Constable at Scripps, and it formed the thesis for Sam Knife, who was a student at Scripps and is now a postdoc at Lamont. And the sort of the cool things that we see from these data, we image a development of fabric anisotropy in the upper crust as the plate bends and faults are induced in the plate. We see fluids penetrating the crust as a result of those faults, and we have been able to put constraints on the amount of fluid within the crust as a function of depth and into the upper mantle. And then also we collected a pretty spectacular image of the 4-arc system, seeing fluids coming back up the plate interface, but also fluids penetrating the overlying plate and possibly hydrofracturing the crust. We're not really clear on the mechanisms yet, but a sort of a pattern of fluids that connect from the slab to the seeps, which are shown in the blue dots on the figure on the lower right-hand corner. So a lot we can do in terms of incoming plate structure, fluid contents of the crust upper mantle, and fluid transport both along the slab interface and out. And then MT, so this is the CSEM result. MT sort of picks up at depths where the CSEM leaves off. And we have images from a lot of work that's been done in Cascadia looking at fluid release from the plate. Some of the sort of the seismic images that Emily showed and Doug showed, we have comparable MT models to those from, at least from Cascadia and some other subduction zone systems. Going on to the next slide, I just want to mention an effort that, you know, Kerry Key, myself, and Sama and Donna Shillington have been involved with for the last few years as a proposal to work in this Samedi-Shumagin area, looking at differences in the hydration of the incoming plate related to seafloor morphology and links between slip behavior and water distribution. So all of the kinds of problems that Emily and Doug have talked about in terms of the incoming plate is an effort that we've been pushing for the last few years, and we will push again. We've been unsuccessful so far, but it's certainly something we're going to go, and hopefully this effort will give a little bit of a boost to our proposal. Couple of points to make clear in the context of this this effort is that NSF have made it clear that anything that is not seismically actually directly related to the deployment of OBSs will need to be done as a separate proposal. I'm not quite sure what that means in terms of how things will pan out, but there it is. And then also from the point of view of TA on shore, I have a question into NSF as to whether Earthscope would envision supporting land-based TA work, MT TA work, and I don't have a response to that yet, so we'll see how that goes. And I think that's what I have got, so we can move on to the next speaker.
Okay, this is Jeff. Jeff and Andy, could one of you confirm that you can hear me?
Loud and clear.
Live. Good.
Okay, great. Let's go on to the next slide then. So Emily talked a lot about the science problems. I'll be pretty brief and focus on how geodesy can help with some of those. The main problem that geodesy would contribute to here is really the questions about the distribution and mode of slip on the plate interface. Geodesy can measure fairly directly which parts of the plate interface are locked, that is, that are not slipping and presumably are eventually seismogenic, which parts are steadily creeping, and which parts may transiently creep, at least if the transient occurs within the time period that you're measuring. So these are things that we can address. The big questions, of course, are why is this behavior the way it is? And so that's our key scientific goal, is to understand why. What we can do with geodesy is measure what it's doing and combine that with other information to try to get at the why. So I'll say briefly a little bit about two ways in which geodesy could be involved in such a community experiment. The first, it would be geodesy integrated with the OBS deployment, and this would be absolute pressure gauges on some or all of the OBSs themselves. And then the other would be geodesy augmenting this deployment, and that would be GPS acoustic, or using GPS on land or additional GPS on land. Next slide, please. Okay, so this is a view of steady velocities of sites within the Alaska Peninsula region. The black vectors are the horizontal motions, and the red vectors, where they are present, are the vertical motions. There is a cutoff for uncertainty, so not every site has a red vector on it, and some of the red vectors are really, really small because the horizontal or the vertical motions are small. The yellow dots show the continuous plate boundary observatory sites. So I didn't actually extend this figure fully to the Cook Inlet, Prince William Sound area. That sort of looks like Kodiak in terms of distribution of sites. But if you look at the length scale, the spacing between continuous sites in most places is pretty large. So we're looking at 75 to 100 kilometers in general spacing between sites. The other little diamonds are campaign sites, and a number of those in the Shumagins and Samitis should be reoccupied shortly through a geoprisms project that I already have. So we will have more information for those sites and more precise velocities. If you could hit the next, it should be, yeah. So another key point here is that at least southwest of Kodiak Island, the GPS time series show essentially linear motion with time over about the last 20 years. Now, not every site runs for 20 years, but there are some that overlap or complement each other in time, and deviations have been relatively small. So there have not been substantial slow slip events identified in this region, at least again through the Shumagins and Samitis and to the western extent of this particular figure. There have been some earthquakes in Kodiak, and also have been a couple of potential slow events identified in the Kodiak region, and some very, very large slow slip events identified in the Cook Inlet region. Next slide, please. All right, actually I'll just go ahead and skip this one because Emily has really already talked about it. Go to the next, please. All right, so let's get into some specifics. Absolute pressure gauges are already integrated with some or many of the OBS instruments. I don't know the exact number of them, but it's something that is already present in a number of cases and could be added in other cases. What these are, the bandwidth covers, at least for the Lamont instruments anyway, covers from about 1 hertz to essentially DC offset. And so these are useful for measuring vertical motions caused by events, by earthquakes that were large enough or slow slip events that were large enough. The instrumental drift is too large to measure slow interseismic deformation at present. There are ways in which you can get at that, but you need essentially to reoccupy points in a campaign type mode, or to use an ROV or something like that to get some calibration so that you can remove out the drift. So that's probably something that would not be totally integrated with the OBS deployment. So in terms of the application to Alaska, if we're talking about the Alaska Peninsula, we haven't identified slow slip events. If absolute pressure gauges were put out, they would be essentially recording if there was a substantial earthquake that could record something. Otherwise, they might not. Or they might record something that we didn't realize was there because it has such a short time window. And in Cook Inlet, there are certainly identified slow slip events, but they are long-lasting, lasting for years, and so actually, again, the drift issue would be a problem. So primarily, we would be looking for events, and it would be more of an opportunistic approach, I think, using these instruments. So it's not a reason not to use them, but it makes them not the primary rationale for any particular deployment of a site. Next. And the other is to look at the problem of resolution for slip. These are 2 figures that come from Rob McCaffrey. They are 2 different slip distributions, or rather lack of slip distributions. So the red colors indicate parts of the interface that are locked. The blue colors indicate parts of the interface that are creeping. These 2 distributions of creep actually fit the data on land in Cascadia about equally well. As you can see, they look rather different. And essentially, the one on the left makes the assumption that the that the interface is locked out to the trench, and the one on the right does not. So this is an indication of the lack of resolution that commonly comes from these sorts of inversions in the offshore region. If we could go to the next slide, which is the last one for geodesy. I've highlighted here in these orange ellipses possible regions where we might consider GPS acoustic. As you can see, we already have a pretty good resolution there's islands in convenient places, so measurements on land allow us the potential of having pretty good resolution in some spots. But if you look over at the west end of, maybe somebody can gesture with the mouse over at the very western end of the region, yep, in there's essentially no strain whatsoever observed on land. This requires the interface to be almost completely creeping throughout its entire depth. So testing whether or not that is true is important, particularly because this is the likely part of the source region for the 1946 Great Tsunami Earthquake. So here we suspect there may be a locked region out by the trench that we don't otherwise see. In the Shumagan Islands, which is a little bit to the east, the strains there are relatively low and suggest that much of the interface is creeping, although not nearly so much as farther to the west. But it is not a normal, fully locked interface like everything to the northwest of it is. And so again, going offshore would be important to understand what the region near the trench is doing. And then finally, between the Shumagan and Samiti Islands, looking at the transition along strike between a very wide locked region, which is what we see from there to the east, and the more creep-dominated sections along the Shumagans. And then finally, I just highlighted, again, the near trench region out in the Kodiak and Samiti regions. Again, just understanding whether or not the interface is actually locked out to the trench or not. Even though we have data relatively close to the trench compared to other parts of the system, there's still limits to the resolution of what you can see out by the trench. So these are places where if we were to do GPS acoustics, there would be a pretty high bang for the buck. As with the MT, I think it's pretty clear from NSF that this would have to be a separate proposal, something that would piggyback or go along with the OBS deployment. And that's all I've got.
Thanks, Jeff. So I'm just going to wrap up with a couple of things. I think, as you've seen, there's a pretty clear case for the some exciting science opportunities that could be done by an amphibious experiment in Alaska. The opening the door through the recent NSF Dear Colleague letter is allowing for at least an onshore-offshore seismic experiment project to be proposed as a community-driven project. And so the people you've heard on the phone and a few others, essentially the conveners and writers of the workshop we talked about earlier, for the most part all agreed to help host and nucleate a community proposal to do this. And there's a couple of things that, of course, we need all your help to do. One is, the report and the discussion you've heard highlights some critical corridors and regions, but of course to turn that into a real proposal, we need to start putting dots on maps, being very specific about exactly what kinds of deployments, what kinds of arrays, densities, timing, and so forth would be needed to achieve these scientific objectives. And so we're asking for a couple of things. One is we've opened an open community bulletin board for people to contribute ideas, suggestions, specific recommendations, maybe for complementary studies such as the geodesy and the MT that you just heard that could go in parallel with this, how that would work. And then the second thing, people that are actually interested in being PIs on this. We should note that the call very specifically says that this community project does not include analysis of this data. So we're really talking about people who want to be involved in the deployment, but there's a lot of opportunities there, especially if you want to get involved in the offshore work, to join. So what we're inviting people to do is, if you're interested in soliciting ideas, if you're interested in joining the PI team, visit the webpage. sign up. GeoPrisms is hosting this. Also, if you're just interested in staying abreast of what's happening, we'll probably have one more open community email, and then from then on, not deluge the whole world with information about this, but if you're interested, we'll start regularly keeping people apprised of where this is going, how this is being put together. If you want to be a PI, we ask that you try to contact us by May 15th so we can really start putting a proposal together. This page also has links to a couple of important documents, all the science planning documents we've talked about. The Dear Colleague letter, that's NSF 16061 is there. There's also an FAQ that NSF has put together in response to some questions people have had that help clarify. That's there as well. And we'll put a video of this webinar on there. Perhaps it'll also show up on YouTube. We'll see. As the project develops, we'll try to keep this posted as much as possible. We're trying to make this as open a community project proposal as possible, given the fairly short timeline between the release of the Dear Colleague letter a few weeks ago and the likely proposal deadline. They're shooting for the GeoPrisms deadline, which is nominally July 15th, although I guess the RFP solicitation hasn't come out yet, so we're not 100% sure about that. That's sort of all we had. I apologize for running a bit late, and thank all of you for sticking with us. As Andy said, he's been open to questions that he's been collecting. And I think what we'll do now is we'll let Andy read to questions, and I'll try to moderate a bit, but hopefully all of our panelists can stay in line to help answer them. Andy.
Okay, great, Jeff. Thanks. All right, so I have a couple questions so far. I encourage people to submit them if you still have them. And the first one's from Colton Liner, and Colton asks, are the OBS stations equipped to handle a nearby magnitude 6 or 7 earthquake without clipping or breaking?
That's a good question. I think, like all sort of seismic stations anywhere, there's a limited dynamic range. There are 24-bit digitizers. Most of the broadband stations have been tuned similarly to onshore broadbands so that they're designed to record weak motion, teleseismic earthquakes, small local earthquakes. And so the consequence is that the seismic sensors probably would clip an earthquake that size, that close. There's been some discussion about adding accelerometers to some of these packages. That's probably something worth discussing. There's a window to modify these things, whether NSF would buy into that. It certainly makes sense, particularly for all these instruments that are directly on the thrust zone. And again, all of them have some kind of pressure sensors which provide a different kind of data that hopefully would maintain scale in the event of a large motion. Does anyone, other panelists, want to comment further on this?
As I understand it, the pressure sensors would definitely remain on scale, but they're only effectively measuring vertical displacement.
Okay. Anybody else have any other wisdom here?
Yeah, I think that's consistent with my understanding, Jeff. You know, I would expect the instruments to clip based on what I've seen with similar OBSs elsewhere.
And I do want to add, this is Susan, that this was recognized even when the Cascadia initiative, the first planning group, right? I mentioned that they were talking about the design, and there was a push to have accelerometers, and so yeah, it's a deficiency, I think, that we recognize in the equipment.
Well, and I think this is Emily now. It might just also be worth mentioning that there are these OBSs with accelerometers do exist. There are, I think, 10 at Woods Hole. I'm not quite sure if they're a part of the OBS IP pool or if they're in a different pool, but it's some do exist, and they were used in Cascadia, I believe, at
Yeah, I think those were the ones that Jeff McGuire and John Collins built with the Keck funds, I think. Is that right?
Exactly. Yep, those are the ones I'm thinking of. So I might be asking if those would be available in Alaska.
I think they are in the pool.
Yeah.
Okay, so that's a good question and something to bear in mind moving forward. Andy, what else you got?
Okay, so we have another question from Sean Way, And Sean asks, it seems like the Alaska Peninsula and Aleutians have a much higher demand for an amphibious deployment. However, the TA is not building any more new stations in that area. All the stations in those regions are existing. So what's the relation between the TA and this proposed amphibious array? How can most TA stations further inland in Alaska be complementary and helpful to our scientific goals?
So my 2 cents, and we'll do this, turn this over again to other people. The TA has actually funded a lot of upgrading of a lot of those sites. Some of those sites had not been working for a long time. These are things that, out on these outer islands near the coast and so forth. Some of them had been with other kinds of equipment. And there have been a few holes that the TA has filled. So I think bringing the TA to Alaska, even on the coastline, has done a lot. But certainly if you start to think about some of the larger scale flow problems and imaging problems that Doug touched on, having sensors far into the back arc could really provide us a window into subduction processes that we've seen at few other places. A lot of subduction zones, there's a volcanic arc, and it's, for various reasons, it's hard to get into the back arc, or there's a back arc rift. I think that there are going to be some important things that we can learn from that. Anyone else want to comment?
Yeah, I'd
Jeff,
agree
I'll
with
just add the.
Yeah,
why don't you go ahead and I'll
yeah.
follow.
I'd agree with you, and particularly there's a lot of TA instruments in that section of Alaska that's just north of the Alaska Peninsula that are TA instruments and weren't there previously. So, and I don't know how many of them will be adopted or stay. So, in my mind, having this happen when you have all those stations in the back arc area will really help a lot.
Jeff.
Yeah, just the same thing. The back arc stations are new, and in many cases the upgrade was from an analog vertical component sensor with extremely limited dynamic range to a broadband. So actually, from something that was usable only as a P-wave detector to something that you can actually use the entire waveform. So so there are pretty significant upgrades, and although not necessarily a large number of new stations in that segment.
Great, Andy.
Okay, this is the last question I have so far. This is from Joseph Burns, and Joseph asks, how many OBSs total should be expected for the offshore array?
So for Cascadia, the array was focused on the instruments that were built through the RF funds. That was 60 total, including 20 of those shallow water trawl resistant mount instruments. What NSF has told us is that we should not see that as a restraint. That is, anything that's in the complete OBS instrument pool is available. So potentially we could have a larger number, significantly larger number, although all the other instruments are really designed for deep water use. So probably for shallow water, we're for the most part limited to those 20 instruments plus a couple of others. Doug, do you want to?
That would be my thought. The big limitation is number of shallow water instruments, and I think there's also maybe we'll have to see how extensive of a project NSF wants to fund. There's been a lot of discussion about whether they'd be willing to fund a 2-stage deployment or just a one-shot deployment. So and so far they haven't sort of really answered that question, or they've answered it in like, well, you can propose more, but we may not fund more, or sort of that kind of response. So and the advantage of a 2-stage deployment, like Cascadia essentially had 4 stages. 2-stage deployment would allow you to more maximize the shallow water instruments that are very limited.
Right. So Andy, anybody else?
Yeah, so I have another couple have come in. One's from Luciana Estes, and she asks, are there any thoughts on deploying OBS stations north of the Aleutian Islands to extend the TA further west?
Interesting idea. It had, I mean, I think when you get far out to the oceanic arc, that was one of the target areas for the certainly the subduction cycle volatiles. This is one of the world's classic oceanic arcs, and one of the few without, a major back arc rift system or a mountain belt behind it. So in that respect, yes, I guess, again, this gets to the shallow water use. It's a very, very wide Bering Sea shelf up there that you would need to traverse. And so to the extent that you're limited by shallow water instruments, that seems like an issue. But it's certainly something to contemplate. Anyone else? Okay.
Yeah, I basically agree that it depends sort of on exactly where we put the experiment, but if we put it in sort of the Aleutian megathrust area, then I think because the number of shallow instruments would be so limited, and you'd want those all in the forearc, it'd be unlikely that that we'd have enough to deploy behind the arc, and that for behind the arc, we just have to rely on the TA. Once again, it shows how important having a TA there at the same time is, because you actually get coverage on the other side over much of that area from the TA. If we ever were able to do an experiment way out, where the second subduction factory site is, out by where the 1957 earthquake occurred, then you definitely want to put OBSs on both sides, because otherwise you couldn't image the arc.
Right. Okay, Andy.
All right, I have another one from Joseph Burns, and he asks, Cascadia went far offshore. Is there any push for OBSs farther offshore in Alaska?
So, no, it's an interesting question. I mean, and that's where having access to the rest of the pool does actually get you something, right? Because then you're in deep water and it becomes easier to get there. I think thinking about what that science motivation is, what the questions are, and structuring that would be important. But certainly, some of these questions, I mean, in my mind, some of these questions Doug was raising about hydration of the incoming plate and so on, probably do require getting at least a ways offshore. The thing to remember too, the scale on this map that I have up here, I mean, this is a big scale, right? That 100,000 kilometer long bar in the lower left corner is longer than the entire Cascadia system. So, you won't look like you get so far offshore to get farther away than the Juan de Fuca Ridge is from the deformation front in Cascadia.
And Jeff, I'll say that one of the reason that there were OBS that far offshore was one of the science objectives was to image the entire Juan de Fuca plate. So, that was required to meet that objective.
And you had a spreading center out there.
Right.
I mean, I think here, basically the plate bending faulting, if it's like what we see in other arcs, goes out about 100 kilometers, and I think you'd want to have OBSs out further than that so that you can, well constrain the structure of the incoming plate in terms of its anisotropy, before it starts bending and perhaps is altered by faulting and so forth. So that means you'd want to go out 200 or 300 kilometers, I think, into the incoming plate. But I can't really see why you'd want to go way out.
But I would encourage if someone has a good idea to write it down, send us something, and we can get that up posted for discussion. Sorry, Jeff.
One more thing. If you look over towards the eastern end of the incoming plate on this particular slide we're looking at, you see some white dots labeled 1987, 1988. Those are high magnitude 7 earthquakes within the oceanic lithosphere. And so that's a place where the oceanic lithosphere is starting to fragment, probably associated with essentially a collisional processes going on in south central Alaska. That's pretty far away from most of the areas we've been talking about. but that is something that people might want to think about either for this or for some future deployment. The oceanic plate is essentially breaking up at its eastern end in the Gulf of Alaska. So there still are earthquakes recorded there on a regular basis, but of course only by stations on land. So there are targets that are out there for for looking at deformation of the oceanic plate and non-rigidity of the oceanic plate.
That's a good point. How are we doing, Andy?
We have one more question from Chuck Esterbrook, and Chuck asks if this group has thought about, excuse me, trying to leverage instruments from other countries such as Germany, Great Britain, France, Japan.
There's been limited discussion so far. We've been focusing on this thing, but it is a great idea. I know there's, for instance, some German projects going on in the far western Aleutians, then into Russia on that side, and I think as this takes off and gets off the ground, having more discussions with people like that would be really worthwhile. And I know that I don't know much about it, but I think people who have been looking into doing large-scale active source work in the central and western Aleutians have also been engaging with some international partners to explore possibilities. That's my vague answer. I don't know, someone else know anything? Any other panelists?
Well, I mean, I've mentioned the project, vaguely to Japanese investigators, and I think there's there may be some interest, but nothing sort of, remotely concrete at this point.
But that's a good idea, and again, that'd be something, if you want to, Chuck, if you want to contribute something to the bulletin board that might actually help spark and engender some discussion along those lines. So Andy, is that everybody?
Well, Bob Stern had typed in somebody's name, and then when I was clicking on the question to read the whole thing, I accidentally deleted the question. Oh wait, he resubmitted it. Koichi Suyehiro at Jamstech is, I think, somebody from Japan that's interested in this area.
Yes.
Yep.
Good.
And that's it from my end. No other questions.
Okay. So, yeah, I mean, I'm just going to say again, we're eager for people who are interested in being involved in this sort of thing to join the PI team. I think there's a lot to do here, a lot of opportunity. Certainly, if you have OBS experience, it'd be great to have you involved. If you don't have OBS experience, it'd also be great to have you involved. If you don't want to be a part of that, but you have ideas, or if you have about how to do this deployment, things to focus on, if there are specific corridors, places, we haven't really talked about dense versus aerially extensive coverage, but anything like that would be hugely helpful to contribute to the bulletin board. I will probably moderate and post these things as they come in. And even if you're not interested, sign up. We'll keep you apprised of progress here. Anybody else? Susan, do you want to close this out?
No, the only thing I want to say is that, we are this group because we were involved in writing the workshop report, and thinking about and synthesizing what ideas came out at that. So we are not the chosen PIs. We're not, we're really looking for this to be an open process and to get people and other people and involved. I mean, it's not, there's no set, we're not just saying, oh, we're looking for one or two additional people. That's not the case at all. And we want this to be, as open a process as it possibly can in the limited time. The negative thing is that we have to do this. The proposals, the deadlines that we're targeting, I think, at least immediately, is probably geoprisms, which is, we don't know exactly when, but probably July 15th-ish. So that is a short timeline.
And I might also, this is Emily, I might also just add that I hope the other panelists agree with me here, but that if you're thinking about submitting something else, as a different proposal, sort of like what Rob was talking about, I think it would also be really great to hear from you and be able to kind of coordinate a little bit as a community experiment science goals are being formulated. So even if it's a separate effort or a separate proposal, it seems like it's a worthwhile, in such a large area with so many science targets, it'd be worthwhile coordinating how we can.
Yeah, that's a great point. Okay, so if there's nothing else, and again, Paula, thank you very much for sticking with us for so long. Hopefully this has gotten you excited about Alaska and about some of these opportunities. And hopefully we'll hear from a number of you soon. That's it.
Thank you, Jeff.
All right.
Yeah, thanks, Jeff.
Thank you. Thanks, panel.
Bye, everybody.
Bye.